Dale, today we're going to start our discussion on the normal model, and this is something we're going to use throughout the year, and we will add to it next lesson. As you can see, this is part one. This is part one of two for now, but we're going to use the normal model and these ideas for the rest of the year. So the first thing we want to talk about is a z-score, sometimes referred to as a standardized test statistic. And so for us right now in application for this lesson, our standardized test statistic, we are going to call Z. We talked in class about the difference between a statistic and a parameter. A statistic comes from a sample. A parameter represents a piece of information from a population. We represent our statistic that we'll talk about today as mean, so X bar, that comes from a sample. And a parameter, the mean for a population is that Greek letter mu, pronounced mu. It's like a funny looking U. Our standard error in this case will be our standard deviation, and we will use the population standard deviation little sigma. So a z-score helps us to compare two things that in any other way don't really have a direct comparison. So here we have scores for French and math exams. And this student, we want to know how did she do on her French test compared to everyone else, as well as her math test compared to everyone else, and which did she do better as it relates to the rest of the students who took those tests. So an 82 and an 86 sounds similar, but these are two different subjects, two different ideas, two different tests. And so what we can do is we can standardize these values. And so her scores, the 82 on French and the 86 in math, those are our statistics. And actually, I should go back here and change this, not X bar, just X. And then we have our means. Whoop, that's a standard deviation. I'll put means in red. And then we have our standard deviations. I'll do those in blue. So we can calculate z-scores for both of them. So for French, we will use our formula. And so she scored an 82. We're looking for a Z. She scored an 82. And she got the French exam had an average of 72 with a standard deviation of 8. And for math, she scored an 86. Subtract away the average on math of 68 divided by the standard deviation of 12. And I'm going to pause while I calculate this. So we have a z-score for French. Sorry, I changed up colors. And for math, the z-score for French is 1.25. The z-score for math is 1.5. What this z-score represents, this standardized test statistic, is the number of standard deviations that her score is away from the mean. And so when it's positive, that means she's 1.25 standard deviations above the mean for French and 1.5 standard deviations above the mean for math. In this case, being above the mean is better. That means her score was better than the average score. And so a z-score of 1.5 is better than a z-score of 1.25 because she scored higher above the mean on the math test than she did on the French test. So she did well on both tests, but relative to her peers, she scored better than the average student by a higher amount on math than in French. And so that's an important reason that we use z-scores, standardized test statistics, so we can compare two groups that necessarily don't have a comparison otherwise. And so that brings us to our discussion of the normal model. We have this curve that is symmetric. It's unimodal, meaning it has one peak right there in the middle. It's got two tails, one to the left, one to the right. Some people call it the bell curve. The area underneath this curve represents probabilities, and the proportion of the area underneath the curve represents a probability, and we can use those probabilities to find answers to questions. We call the middle a z-score of 0. And then we go to the right 3 standard deviations. So we'd say z equals 1, z equals 2, z equals 3. And then the same thing to the left, z equals -1, z equals -2, z equals -3. So 1 standard deviation above the mean, 2 standard deviations above the mean, 3 standard deviations. And what these percentages mean is that if we have data that follows this normal model, that looks like a normal model, it's symmetric and unimodal, that 68% of the data points will fall within 1 standard deviation of the mean, above or below. So this area in the middle represents 68% of the data points. Within 2 standard deviations of the mean, -2 to +2, that's 95% of our data points. Approximately, these are approximate values. And then between 3 standard deviations below and 3 standard deviations above, almost all, 99.7% of our data points will fall into that range. And so you can see there's a little left over, so these go on further, but almost all of our data points, when we have a normal distribution, will fall within 3 standard deviations of our average value. So 3 standard deviations above, 3 standard deviations below. And typically we would say that anything that is above 2, so anything from this point to the right, or anything below 2 this way to the left, anything in those pieces, those tails, we would call those unusual. Because frankly, there's just not that many of them. These two tails represent 4.7% combined of all of our possible data points. And so anything that falls in those spaces on our normal model, we would consider an unusual value. Not impossible, but unusual. So this is what we call the standard normal curve, because we use standardized test statistics, z-scores, to draw it. But we can draw normal curves with data points. And so I'm going to pause here, and I'm going to draw the normal curve for this and then explain it to you. So what I did was I sketched a symmetric unimodal distribution, and you can have a little laugh because there's nothing symmetric about this, but this just shows you that a sketch is a sketch and it will be helpful even if it's not perfect. This is quite imperfect. I took the mean gas mileage for this scenario where we are measuring fuel economy on automobiles. The mean we'll put in the middle. And then I added 3 standard deviations to my mean, and I subtracted 3 standard deviations from my mean. So to get from 24.8 to 31, I added 6.2, and then 6.2 more, and then 6.2 more. From 24.8, I subtracted 6.2 3 times to get these 6 values that represent 1, 2, and 3 standard deviations above and below the mean. And so therefore, quickly, between these two values, 68% of our automobiles would fall between those two values on their fuel economy. 95% will fall within 12.4 and 37.2 miles per gallon. And then almost all, 99.7 of our vehicles' miles per gallon will fall within 6.2 miles per gallon and 43.4 miles per gallon. And again, just to point out this idea that in this tail and this tail, those represent unusual gas mileages because they are more than 2 standard deviations away from our average gas mileage. They're not impossible gas mileages, but they would be unusual. So a gas mileage of 6.2 miles per gallon on a vehicle would be very unusual, though not impossible. And so what we can do with these sketches, and I'm going to see if I can get the question in the sketch, is we can find a percentage if we're given in this case, a miles per gallon of a automobile. And this can give us a probability or percentage of automobiles that would get more than this amount. And so these pictures help us because we can go to our drawing and we can find 31 is right there. And we will be finding this area to the right. And we can do that using the calculator. And so what we're going to do is we're going to hit second vars, and we're going to go to the second option, normal CDF. It's going to ask for an upper and a lower bound. What we're telling the calculator is what number goes on the left of the area I want to know and what number goes on the right of the area I want to know. So on the left of my area is 31. On the right of my area, this thing technically goes forever. So we do 1 e to the 99. It's kind of like putting infinity. And then we'll type in our mean is 24.8 and our standard deviation is 6.2. And this is going to give us this decimal. And we're looking for a percentage right now. And so we'll turn that into a percentage of 15.87. And so what that means is, based on our normal model up here and these values we've been given, 15.87% of the automobiles will have a gas mileage of more than 31 miles per gallon. I want you to pause here and I want you to read this problem, and I want you to see if you can sketch the normal model based off the information you're given here, and then I will do the same. So hopefully you got something similar to me. If you didn't, now's the time to call me over or to ask me when you see me. Our mean is in the middle, and then I added 84 3 times, subtracted 84 3 times. And so we can use this to find some percentages about the weights of these Angus steers. And so if I want to find out the percent that are over 1,250 pounds, I can go up here and I can see 1,250 is somewhere in here. Not exactly, I don't know, but somewhere in there. So we're looking for this area. And so we can go tell our calculator second vars. We're going to choose the second option, CDF. Our lower value is this 1250. And it goes to the right, so it goes to positive infinity. So we're going to leave that as 1E99. Our mean, we'll change it to the mean for this problem, 1,152, and our standard deviation of 84. And that's going to tell us that 12.17% of these Angus steers weigh over 1,250 pounds. We can do the same thing for under 1,200. So 1,200 will be somewhere in here. Again, not exactly. This is just a sketch to give us a visual. And so we can do second vars. Again, the second option. You might want to write this down so you remember. This time, our left side is the one that goes to infinity. And so we're going to say this is negative. Let me see. Negative 1 e to the 99. Our right side, our upper is right here, our value of 1,200. We can keep the mean and standard deviation the same for the same problem, and we can get a percentage of 71.61%. So almost a third, 71.61% of these steers will have a weight that is under 1,200 pounds. And we can do the same thing for 1,000 to 1,100. So we're looking somewhere in this area, 1,000 to 1,100. And so we'll do the same thing. We'll second VARs, second option, normal CDF. This time we'll tell it the left side is 1,000. Oops, 1,000. The right side is 1,100. Same mean, same standard deviation. And so we'll find that 23.28% of the steers will be in that range of weight. It is important to point out that our normal model, like we must know that this data is distributed normally. And we could actually use this notation that we have a normal distribution with mean 1,152 and standard deviation of 84. You might see it that way. So this is the mean and this is the standard deviation. And this means we have normal distribution. So I want you to give this one a try, practice sketching the model, practice finding these scores using second VARs on the calculator. And if you do have any issues, please ask. We will go over this problem together. Take your time on this, ask for help if you need it, and of course, good luck.